Greetings, mathematicians. Today we are beginning a topic of graph theory. Graph theory is the first element in our journey through discrete math, and it's different from past maths. It's not that graph theory is in like y equals x squared is a graph of a parabola, or sine of x gets you a sine wave, or any kind of graphing that we've done like on the xy plane in past math courses. Graph theory for us in discrete math is all about the study of graphs, okay, makes sense, and their applications. Now a graph in discrete math, what we're looking at is a collection of these vertices and edges. I'll get to more of those. Over here on the right, and what we saw in class is an example of a graph. Now I mentioned it's a collection of these vertices and edges. Vertex is just a point on the graph. So my graph on the right, we have 4 vertex points, 4 vertices. There's vertex A, vertex B, vertex C, and vertex D. A vertex is a point on the graph. An edge is a line or curve that starts and ends at vertices. Now back to our graph, we have a number of different edges. We have an edge between A and B. So like AB is one edge. We have actually a separate edge between AB. We've got an edge between BD. We've got an edge between AC. We've got an edge between BC, an edge between DC. So in total we have 1, 2, 3, 4, 5, 6, 7 different edges. I can also mention that AC, that edge connecting, starting at A and ending at C, is the same thing, is congruent, is equivalent to the edge CA, starting at C and ending at A. It still connects different vertices. So graph theory is looking at all of these different kind of geometric objects that we call a graph, which are just collections of vertices and edges. Points, or vertices, can stand alone, but an edge always has to begin at a vertex and end at another vertex. Graph theory is just how these are connected and what they look like and what we can do with them. We have a few other special definitions that we do along the way. Since we've got edges, an edge begins at a vertex and ends at another vertex. A special type of edge is called a loop. A loop is one that starts and ends at the same vertex. So over on the graph at the right, I've got edge AD, where I have this edge that begins at E and ends at E. So edge EE is actually a loop because it begins and ends at the same place. I can go from E to E, or I can go from E to E the other direction. Those are both edges, or loops. Additional definitions, we have the degree of a vertex. The degree is the number of edges connecting to a vertex. So vertex A has one edge coming out of it. It has first degree, or degree 1. Whereas if we look at vertex D, the degree of vertex D, we have one edge going to A, one edge going to B, a different edge going to B, and an edge going to E. So there's 1, 2, 3, 4 edges. D has degree 4. We take the others. We look at vertex B. Figure this out, count along with me. We've got 4 edges. Vertex C has degree 2. There are 2 edges coming out. And vertex E has 5 edges. What? Let's count that. There's one edge going from E counterclockwise. There's one edge going from E clockwise. There's an edge to C, an edge to B, and an edge to D. 1, 2, 3, 4, 5. So it has degree 5. A loop, because we can go both directions, counts for 2. And in a way, what I'm thinking about is, if I just zoom in on a vertex, how many lines are coming out? 1, 2, 3, 4, 5. We got degree 5 for vertex E. So that's the degree of a vertex. We can classify those in 2 different ways. Either we have an odd vertex with an odd degree. So vertex A, when we have one edge, or degree 1, and vertex E, degree 5, are both odd vertices. We've got 1 edge and 5 edge, odd values. An even vertex is one with an even degree, 2, 4, 6, 8. So back to that, D had 4, B had 4, and C had 2. Those are all of our even vertices in that past example. So you can see odd, odd, and then even, even, and even. What do we do with these? We're looking at different items right now that are going to be called a path or a circuit. Now a path is going to be any route along the edges that starts at a vertex and ends at a vertex. Just saying I'm at A, I go to B, I go to C, I go to D, etc. Over on the right, I have an example of a path. Starting at vertex A, following these arrows here, I go to vertex D, to vertex C, to vertex A, vertex B. So I have a path that goes A, D, go to C, A, D, C, A, B. That is an example of a path, just a route along, identifying that I'm going from one vertex to another, to another, to another, etc. It can be as simple as from E to D. That's a path, because it's a route along the graph, along one edge, connecting one vertex to another. A circuit is also a type of path. It's any route along the edges, starts and ends at a vertex, but a circuit has this extra special requirement that it starts and ends at the same vertex. It doesn't matter how many edges, how many vertices we go through, but a circuit goes along and closes. Circuits, just like electricity, gets back to the start. My graph here on the right, I'm going to be starting at D, following the numbers, going to B, to C, to A, to B, to back to A, back to D, over to C. Well, that's an example again of a path. I should have checked that at first. I could go A to B to D, back to A. That is an example of a circuit because I've returned back to this starting vertex. And I'm going to be using this, identifying the order of my vertices by listing the letters in order. Now, specifically, we're not looking at just any path, any circuit. Leonhard Euler, the Swiss mathematician that we started talking about in class, we're going to be concerned with Euler networks. Swiss mathematician Leonhard Euler, pronounced Oi, mate. That was terrible. Euler. So not Euler, Euler. Now we're going to be specifically looking at what's called an Euler path or an Euler circuit in these first few days together. An Euler path is a path, so it goes around different vertices, but we're going to cross each edge exactly once. So we need to go around the graph, but we're crossing each edge exactly once. On the right side, I can do that. I'm going to start at vertex A, just because it's the first letter of the alphabet. I'm going to go to vertex B. I'm going to follow the loop, back at B, go into vertex D, go into A. Now, as is, that's a circuit, but it's not Euler. We're going to go to C, and then I'm going to go to D. We have what's known as an Euler path because we've crossed each edge exactly once. Notice that a path, I begin and end at different vertices. Something about that actually tells us we're going to have a path. Now, a circuit, we know, begins and ends at the same locations. An Euler circuit is once again a circuit. It's going to include every single edge. Euler is always about the edges. Include every edge of the graph exactly once. So we need to also return back to the starting vertex. My graph over on the right, if I start at A, I can go to D, I can go to C, I can go to D, that's the letter E rather, go to B, go back to C, and then I can go back to A, crossing every single edge and returning back to the starting vertex. That's an example of an Euler circuit. We're going to be looking for how can we differentiate what kind of graph gives us an Euler path, what kind of graph gives us an Euler circuit, and then sometimes graphs cannot give us either an Euler path or an Euler circuit. For example, I might try this with the graph down to the bottom right. I go from A, go to C, D, F. Ooh, I'd be stuck there. I've already used the edge leading to F. Well, that kind of cues me in that I probably have to start at F. If I go from F to D to C to A, back to D to E to A, ooh, I'm stuck there. I missed that one. If I go from F to D to E to A to, ooh, I'd be stuck at B. I wonder if I can actually find a way around that. Maybe a path or a circuit. Well, if I start at F, I'd have to leave F. But then I also have to finish at B. All right, so B has to be the last one that we go through. F, D, okay, maybe if I make my way all the way around, I'd either have to go to A or I'd have to go to B. We're going to think about that one. There's our example. Those are the notes. Those are our definitions that we have so far. See you later.